Okay, let's try this problem. Here, we're supposed to determine whether the titration between a weak acid and a strong base will have an equivalence point that's acidic, basic, or neutral. And then we're supposed to go ahead and calculate the pH at equivalence if 50 milliliters of a 1 molar weak acid, acetic acid, is titrated with a strong base that's 2 molar sodium hydroxide. They give us a Ka for acetic acid as 1.8 times 10 to the minus 5. All right, so let's start with the very beginning. What's our prediction? If we titrate a weak acid with a strong base, we predict that we're going to get a basic equivalence point. Now, just because we have a strong base, that's not what makes it basic at equivalence. In fact, when you reach the equivalence point, the weak acid and the strong base will both be completely used up. They no longer exist, so that's not why it's basic. It's what they turn into. The strong base will turn into a nothing conjugate after the reaction. We're not going to worry about that part. It's going to be neutral. But the weak acid, when it reacts, will turn into a weak base. That's why we're going to have a basic equivalence. Now, let's go ahead and write down our data, and then we'll begin the problem. So we have some information for our weak acid HC2H3O2, and we also have some information about our strong base sodium hydroxide. I'm just going to go ahead, make a little T-chart, and write down the information I have for both of them. Here's what I know so far. I know for my acetic acid, HC2H3O2, I know that I have a volume of 50 milliliters. I'm going to change that into liters right away. I know I'm going to need liters, so let's just go ahead and do that. 0.0500 liters. I also know the molarity of this is a 1.00 molar solution. Okay, now what else do I know? I know the molarity of my sodium hydroxide is 2.00 molar. I don't know the volume yet. I probably am going to need it. But what can I do with this? Well, if I have a molarity and a volume of my acetic acid, I know I can find the moles. Moles is always molarity times volume. So 1 times 0.05 is simply 0.05. So I can go ahead and plug that in, 0.500 moles. All right, now, the key to this problem is that if you are at equivalence, the moles of your acid and your base are going to be equal. So if I know that we have 0.0500 moles of the acid, I also know that we have 0.0500 moles of my base. Those will always be equal at your equivalence point. All right, with that, if I have moles and molarity, I can determine how much sodium hydroxide I actually needed in order to reach that equivalence point. I don't technically need that yet, but I know I'm going to need it, so I might as well do that right away. I know that moles equals molarity times volume. So the volume is going to be equal to, divide both sides by molarity, moles over molarity. The volume is equal to my moles, 0.0500 moles over a molarity of 2.00 molar. And if you go ahead and plug those in or divide those into your calculator, 0.05 divided by 2 is 0.0250 liters. So I'm going to write that in right here, 0.0250 liters, and that actually makes sense. If you needed 50 milliliters of a 1 molar, that could be titrated by half as much, 25 milliliters of a 2 molar, since it's twice as concentrated. So here's all our data for our titration. Now they're asking us a pH calculation. Always start off with, what do you have? Identify what you have. You have an acid and a base. This acid and base are going to react. So the plan of attack, write the reaction, react them in moles, and see what's left. So let's go ahead and start with that right now. I'm going to go ahead and write my reaction. My reaction is between H, C2, H3, O2. We're going to react that with our sodium hydroxide. When we do our double replacement reaction, we get NaC2H3O2, and we're going to go ahead and get some water. We react them in moles. I know for each of those, I have 0.05 moles. So I have 0.0500 moles of my acetic acid and 0.0500 moles of my sodium hydroxide. Because this is equivalence, they both get used up. We're supposed to react those perfectly. So I'm going to subtract 0.0500 moles. I'm going to subtract 0.0500 moles. I'm going to add 0.0500 moles. Now, what is left over? We don't have any acetic acid. We don't have any sodium hydroxide, but we do have 0.0500 moles of sodium acetate. React them in moles and see what's left. Great. What is sodium acetate? Sodium acetate is a salt. We have a plus minus salt. Now, what part can we cross off? We can cross off our big B cations. That sodium ion is unimportant for our pH. That simply leaves behind an anion. And this is a weakly basic anion. Remember, we're supposed to be basic at the equivalence point. The strong turned into nothing, and the weak acid made a weak conjugate base. So we have a weak base. What is our plan of attack for a weak base? Put the base in water, ice it with a KB for a base. Now, the problem is, if we're going to use KB expressions, equilibrium expressions, those must be concentration based here. We need to go ahead and have the molarity of this base. Right now, I don't have the molarity of my base. I only have moles. So before we go further, let's change that back into a molarity. So our molarity is going to be the moles here divided by the liters, right? Molarity is always moles over volume. I have the moles right here. I just need to divide it by the total liters of my solution. So if I go back up and look, I've got liters from my acetic acid. I've got liters from my sodium hydroxide. We're just going to add those two together. 0.05 and 0.025 is 0.075, 75 mils right here. So we're going to use 0.0750 liters. Now, if you go ahead and divide that, that's basically 50 over 75 or 2/3 here. So you end up with a molarity of 0.667 molar for that acetate ion right here. All right, now we're going to need to go ahead. We have a weak base. Remember, the plan of attack is take your base, put it in water with some ice, and a KB. So let's go ahead and do that. But I definitely need more paper here. So give me a moment. These problems are long, they're burly, but I kind of love them. So let me just record what we had. We knew we had a molarity of that acetate of 0.667 molar. All right, again, let's take that base, put it in water. C2H3O2 minus. We're going to add that to some water. Now we're making an ice table. This is only a weak base. So for a weak base, let's go ahead, use those equilibrium arrows. My base accepts a proton to make H, C2, H3, O2, and we're going to leave behind some hydroxide. Now, in the ice table itself, the initial value here is 0.667 molar. I'm going to take away X add x, at equilibrium we'll have x, and I'm going to go ahead, rule of 100 this x away and call it basically 0.667 molar. All right, we have a weak base. We iced it, we need a KB. If you go look in your problem, you don't have a KB, you have a Ka. So another step we have to take, we have to go ahead, change that Ka into a KB. You know how to do all these steps individually. We're just putting everything together. So your KB is going to be 1.0 times 10 to the minus 14th all over the Ka value they gave you. This is 1.0 times 10 to the minus 14th all over the 1.8 times 10 to the minus 5. That gives you a value of 5.6 times 10 to the minus 10. All right, we have our KB. That KB value is going to be equal to your products over your reactants at equilibrium. So we're going to take our 5.6 times 10 to the minus 10, set it equal to x times x, or x squared, all over the 0.667. All right, cross multiply here, 5.6 times 10 to the minus 10, multiply by 0.667, take your square root. You end up getting a value of x equal to 1.9 times 10 to the minus 5th molar. And then we ask, okay, great, we have x, but what is x? Coming back up, x is the hydroxide concentration. We know the OH minus. So if we know the OH minus, we should be able to go not directly to pH, but how about a POH? The POH is negative log of the OH minus. Negative log of 1.9 times 10 to the minus 5. Now, if you go ahead and evaluate that, you know it's going to be very close to 5. It's going to be between 4 and 5. In fact, I get a value of 4.71. So close. All we need to do is change that POH into a pH. And we can do that by saying the pH is 14 minus that POH value, the 4.71. And if we do that, I get a pH value of 9.29. And as predicted, that is a basic pH at equivalence. I hope that helps. Take care.